Hello friends. So let us resume our discussion on representing the creep behavior of the material and understanding it as well. So in the previous lecture we saw that the conventional way of representing the creep behavior would involve strain versus time plot. So in this, what we do is we consider the strain along the y-axis while we consider the time along the x-axis. So given that the creep is nothing but time dependent behavior of the material, that is what creep studies, we use this approach, or this is being used as a conventional way of presenting the creep behavior of the material. While presenting the creep behavior using this in this framework, what we assume is that the mechanical load that we impose on the material is constant. Now one can ensure that the mechanical load that we impose is constant by imposing or applying a constant load all through the testing process. However, there might be the possibility that towards the end of your testing, the cross section of your sample might decrease. So when your cross section decreases, ultimately that would increase the stress. So even though overall, when you consider your apparatus, even though you are applying constant load, locally with respect to the material, there is an increase in the stress, and therefore the mechanical condition that you assume to be constant is no longer true. Therefore, in order to ensure that the constant condition or the mechanical condition which is it's applied, a constant mechanical condition is applied, we instead of assuming or instead of imposing a constant load, what is usually done is we ensure that the stress experienced by the material is constant, particularly not with respect to the original cross-sectional area but the instantaneous cross-sectional area. So when we consider this plot here, a two-dimensional plot involving the strain and time, what we implicitly mean is the mechanical condition in terms of stress with respect to the instantaneous area is assumed to be constant all through the testing period. Now we also saw that from this conventional plot, we can arrive at the slope, or we can arrive at the creep rate versus time plot. So this creep rate is nothing but the slope of this curve. So we have a conventional curve involving strain and time. The slope of this curve is nothing but the strain rate or the creep rate, and you can plot this change in the creep rate over the period of time. So one way of doing that is calculating the slope of the conventional curve and plotting it. However, there is another way of doing it, meaning if you have a very precise equipments or apparatus that could measure the strain over a small period of time. See, we consider a time dt that is close to 0, and in this period of time you have an apparatus that could accurately calculate the strain exhibited by the material or the creep strain exhibited by the material. Since we are talking in the context of creep behavior, whenever I say strain, it is synonymous to creep. So please do relate those terms. So if you have an apparatus that is sensitive enough to capture the very small amount of strain exhibited by the material for a very small duration, then you can directly calculate from the experiments you do, you can directly arrive at this plot which considers the change in the strain rate over the period of time. Now you can also plot the same curve in a different manner, wherein you replace the time with the overall strain. Now instead of considering the overall time during which the material exhibits the creep behavior, you relate it to something that is relevant to the material. So time is an independent factor. Instead of that, you relate it to the material itself, you relate it to the overall creep behavior of the material, and that is one way of representing the same plot. The change in the creep rate is now being represented in terms of the overall creep instead of the time. Now in all these three ways of representing the creep behavior, we assume that, so there is a unifying factor, we assume that the mechanical condition that we impose on the material is constant all through the testing period. Now another way wherein this assumption is disturbed and a new assumption is introduced is the condition wherein we assume that the strain rate is constant all through the testing period. Now when we assume that the strain rate is constant, we have to impose sufficient amount of mechanical condition that would ensure this criteria. So we define our test in such a way that the strain rate should be constant all through the testing period. Now in order to achieve that, we have to impose sufficient amount of load or mechanical condition that would ensure this criterion. Now we have seen that over the period of time this strain rate would vary. So this data we will get from this, or this information we can get from these two plots, that with time during the creep behavior the strain rate would vary. So correspondingly, in order to ensure that the strain rate is constant, your mechanical condition that you impose should also vary. So that is one way of representing the stress strain curve. So instead of assuming strain related components along the y-axis, one way of ensuring that you introduce a new way of representing the creep curve is by considering a condition wherein the creep rate is assumed to be constant and the mechanical condition that is required to keep this creep rate constant is plotted with respect to time. And of course, you can also replace the time here with the overall strain exhibited by the material, and this again would then provide a plot wherein instead of objectively talking about change with respect to time, we can subjectively talk in terms of the behavior of the material, the stress and the behavior of the material. This would more or less be related to the stress strain curve that you usually associate with the mechanical behavior of materials. So these are the different ways that we have seen one could plot the creep behavior of the material. And in the previous lecture, we tried to convince ourselves that the best way to, or a rather more preferred way of presenting the creep behavior would be the conventional strain versus time plot. This is because you can talk about, because of the definition you could prefer this, and numerous ways you can talk about this. We have done so in the previous lecture. But when you talk, or the one convincing one is that whatever test we do, we want to do it in view of a particular applications that we want to serve. And in that view, when you talk about which of these different representation would be most preferred, then the strain versus time plot will be preferred, because when you talk about a mechanical condition in an application more than the strain rates, the load experienced by the material in that application is easily discernible. So from that point of view, when you present your creep behavior in terms of the conventional way involving strain versus time, it is the information that it delivers is more appropriate for the application. And that is the reason why this is termed as the conventional way. This has become the conventional way and people are preferring it. Now, so far what we have not done is we have not related the behavior of the material that is responsible for the different stages of the creep. We saw that the conventional creep curve, or in a crystalline material, when you impose a constant mechanical condition to it and you allow it to deform over a period of time at a particular temperature that is greater than or noticeably greater than the ambient or the room temperature, then under these conditions, that is the temperature is constant and the mechanical condition that you impose is constant, we saw there is a representative creep behavior that is exhibited by the crystalline material that would involve definite stages. We saw these different stages can be categorized either as 3 or as 4. So we saw there is an instantaneous creep stage where the creep rate is constant, and this happens at the very instant once you start applying the load. The constant load once you start applying, or the constant stress once you start applying, there is an immediate response to the material, and that we refer to as the instantaneous creep. And following the instantaneous creep, we have a decelerating creep or the transient region. So in this region, the curve of the or the slope of the curve is decreasing, and this we refer to as the transient region or the decelerating creep. And following this transient region or the decelerating creep, what we have is a region wherein the strain exhibited by the material or is rather marginal, Whatever strain is exhibited, if it is exhibited, is rather marginal, and therefore the creep rate is also constant. If there is no strain exhibited by the material, then of course the creep rate will be 0. If it is marginal, it is more or less the creep rate is constant. So this is referred to as the steady state condition or the steady state creep. Now ultimately you have your tertiary creep, wherein the material ultimately continues to deform and ultimately fail. So in this region, the creep rate is accelerating. There is a continuous increase in the creep rate and ultimately leading to the failure of the material. So this is the conventional representation, or these are the different stages that the conventional representation of the creep behavior gives us. And of course we have seen the similar behavior is also observed in the different forms of representing the creep behavior. But this is how we can categorize the creep curve into different stages. Now we have seen the conventional way, even though, or the usual way, even though couples the instantaneous and the transient stages, meaning the stage 1 is usually the combination of instantaneous creep and the transient creep. And moreover, since the instantaneous creep is so much quicker that when you compare it to the overall duration of the creep test, it can be ignored, then the stage 1 would comprise of just the transient creep. We also saw that when you take the purely an English view, according to Professor Dieter, when you think about that, then your creep curve would comprise of 4 stages, and these 4 stages would involve instantaneous creep, transient creep, steady state creep, and the tertiary creep. So these 4 are accelerating creep. So when you talk about the stages of creep and want to place the instantaneous creep at the equal fitting with respect to all the other stages, then the English view, let us say, would comprise of a 4-stage creep curve. So it will comprise of 4 stages, and that means that instead of the instantaneous and transient creep occupying a single stage, the transient assumes a stage of its own, and also the instantaneous creep assumes a stage of its own. So that means the stage 1 would be instantaneous, stage 2 will be transient, stage 3 will be steady state, and stage 4 will be accelerating creep. So these are the 4 stages that we can classify or categorize the creep curve into. Now in this lecture, let us try to see what are the factors that are responsible for these creep curves. Now let us begin by taking a phenomenological approach. Let us begin by considering the instantaneous creep. So the instantaneous creep involves the strain exhibited by the material once you start applying the load. So this is your strain at the time, and this time, as of course it's close to 0, or it's very much very small when you compare to the overall time that is taken for the creep testing. So when you consider this t here with respect to the overall time during which the creep test is being done, so this time is relatively small. So what we are talking here is about instantaneous creep. So instantaneous creep is what we are talking about, and we want to understand what are the material behavior that are responsible for this instantaneous creep. Now since we have a fair clue of what happens when you impose a load to a material, now we can relate that to this stage of the creep and see what are the factors that are responsible for it. We have an idea of how a material behaves under mechanical condition or under imposed mechanical condition. So for that we plot that using the stress strain curve, and we see that the typical stress strain curve would look something like this. It comprises of the elastic region and the inelastic region. Now having known that, if you think about what could be the factors that would be responsible for the instantaneous creep, when you suddenly impose a definite load to it, then you could say the first response of the material would be elastic, meaning there will be a reversible change in the position of the atoms, and this reversible changes will, again, given that they are reversible, this position of the atoms will be reversed and they will get back to the normal position, and once the load is released. So given the sudden impact or the sudden condition of loading, there will be a metastable or a reversible change in the position of the atoms, and given that this sudden application of the load or the sudden imposition of the load occurs at an higher temperature, in addition to this elastic deformation of the material, we have seen that there can also be an anelastic change in the material. So the difference is in the elastic deformation, when you unload your material, the origin or the portion of the atoms which assume a reversible state will get back to its original state, thereby establishing the original form of the material at the given instant. However, in case of anelastic behavior, there is a lag in the when the material tries to reverse to its original position. We saw that there is a lag exhibited by the material. The path it takes is not as similar to that of the elastic deformation, and we attributed that to the grain boundaries that are present in the polycrystalline system. Supposing the material that you test is of polycrystalline nature, then in addition to the elastic behavior contributing to the instantaneous creep, the anelastic behavior will also contribute to the instantaneous creep. Now, the factor that introduces the anelastic behavior into this instantaneous creep or the instantaneous strain is because we are talking about the creep test that is occurring at a high temperature. Now, in addition to this elastic and anelastic behavior, it is also possible that the material can also deform at the very instant plastically. So, there can also be the permanent movement or the permanent location or permanent propagation of an atoms, and thereby establishing a permanent change, and this could also happen during the instantaneous creep stage. So, you impose a load suddenly and there is a behavior that is in a way the material responds, and if you consider what are the changes that is happening during this instantaneous creep stage or once you apply this load. So, there are different ways these materials would respond, and all these collectively would contribute to the instantaneous creep. So, depending on the regions we are talking about, some region might exhibit an elastic change, some region maybe along the grain boundaries in a polycrystalline system might exhibit an anelastic behavior, and some possible regions, some already pre-existing condition might cause the plastic deformation. So, combination of elastic, anelastic and plastic deformation is responsible for the instantaneous creep that occurs once you apply the load. And now, once you arrive into this plastic region, or once your deformation is governed by the plastic region. So, once you by plastic deformation I mean. So, once you initialize the plastic deformation, so we can now talk about when we talk about plastic deformation, when we can then talk about in terms of dislocation. So, once you initiate a dislocation, once the dislocations nucleate and the existing dislocation begins to multiply, then you enter into the region, you move away from this elastic region in the regular stress strain curve and move into the inelastic or the plastic region. And when you want to relate it, or when you want to talk about the plastic region, there is a specific reason why we have a typical curve like this in the, or a typical section of the curve like this in the stress strain plot. This is because it is fairly known to you. Let me re-jog your memory. So, we have this section of the curve is of this typical form. So, this section is perfectly straight. In a general case, this is perfectly straight, and this section of this curve is of this form because once you initiate the plastic deformation, once you start to have dislocations, with increase in the plastic deformation, the number of dislocation proportionately increases, meaning the dislocation density also proportionately increases. With increase in the dislocation density, the migration, the gliding or the propagation of the dislocation that translates into the plastic deformation will be confined. So, let me repeat. Once you initialize the dislocation, once you start your plastic deformation, once the dislocation starts to nucleate, and you continue the plastic deformation, meaning you continue increasing the number of dislocations, meaning the dislocation density continually increases, what it ultimately means is that the propagation of a dislocation that translates into the plastic deformation is impeded. So, that means the amount of stress that is required to facilitate the free propagation or the ability to overcome any obstacles that is present in the plane or the slip plane because of the pre-existing dislocation needs to be higher. So the ability to overcome any obstacle needs to be higher. So that means you need an additional amount of stress, additional amount of energy in order to for the dislocation to propagate easily in the slip plane. Therefore, what we observe is for the plastic deformation to continue, in the general stress strain case, you have to impose an additional amount of load. So that is the reason for this typical manner of this curve, meaning once you initialize the plastic deformation, once the dislocation density continues to increase, you have to impose additional stress in order to ensure that the plastic deformation continues. In our case, we have already imposed a condition that we work under the criteria that the mechanical condition that we impose will not change. So the mechanical condition that we impose is going to stay the same. So in response to that condition, considering that now for the dislocation to move, they need additional stress. However, we are under the condition that the stress that we have imposed is constant. So in combination of these two, what happens is that the strain exhibited by the material decreases with respect to time. So let me repeat. In case of the stress strain curve, what is happening is we refer to it as the strain hardening. So whatever I have been talking about is nothing but the strain hardening. So in order to continue your plastic deformation, once you have certain amount of dislocation density, the amount of stress required increases. However, in our case, the stress is assumed to be constant, and therefore the amount of strain exhibited by the material once the plastic deformation has occurred decreases, and this is what leads to the decelerating creep or the transient region. So the factor that is responsible for this transient region is the dominance of the plastic deformation, particularly the increase in the dislocation density and subsequently the limitations that is imposed by the increase in the dislocation density for the propagation or the gliding of the dislocation that translates to the plastic deformation. Had we been in the condition where we are allowed to increase the stress, then we can somehow rectify the decrease in creep, but we are in the condition wherein we have imposed a definite mechanical condition, a definite stress to the system. So therefore, the rate of creep decreases in this transient region. Now, whenever we talk about dislocation, whenever there is a dislocation that is being formed in the system and with increase in the load or with continual plastic deformation, there is an increase in the dislocation density. When we talk about this increase in the dislocation density of the system in terms of the energy, in terms of the overall energy of the system, with increase in the dislocation density, there is a proportional increase in the overall energy of the system. So this rho here, let us assume that to be dislocation density. So when you continue your plastic deformation, proportionately your dislocation density increases, and with respect to the dislocation density or in proportionate to the dislocation density, the energy of the system increases. Now in general case, we have no ways of decreasing this energy, and we continue imposing the mechanical condition to arrive at a definite state or to arrive at the desired properties. However, if you want to decrease this dislocation density, thereby decrease the overall energy of the system, what would you do? Supposing you have imposed sufficient amount of plastic deformation to a material such that the plastic or the dislocation density has sufficiently increased and it is too much for your desire or for your application, that is too much, then what would you do? If you translate the term plastic deformation to cold working, and if you translate the term dislocation density to the respective properties, then one way to change decrease the number of dislocation density is to anneal it. When you anneal it, the dislocation density decreases and you are able to achieve or establish the properties that you want. So now, when you talk about in terms of cold working, wherein you just impose a plastic deformation, you increase the dislocation density of the material, and now you want to reduce the overall energy of the system to a certain extent, and then you anneal it. So what is essentially happening in the annealing is you increase the temperature of the material. That is nothing more you would do. You just increase the temperature of the material. You will not introduce any phase transformation or anything like that. Just you increase the temperature of the material. Now, when you increase the temperature of the material is nothing but what we consider in the creep testing. So, in creep testing, similar to annealing, we are not talking about an ambient temperature or the room temperature. We are talking about a relatively high temperature. So, ultimately what you are doing is you are introducing a condition that is similar to annealing during the creep testing itself. So, therefore, whatever dislocation has been introduced by the load can also be annealed during the creep testing because of this increase in temperature. So, when we talked about there is a plastic deformation introduced by the load, and because of this plastic deformation we have strain hardening. Because of the strain hardening, the rate of strain decreases. So far what we have been talking about is purely from the point of view of the load that is applied to the material. Now, in addition to the load in creep testing, we have a contribution from the high temperature, and this contribution from the high temperature can be related to the annealing which we are familiar with, which we can relate to. So, in annealing, in order to reduce the energy of the material that is caused by the higher number of dislocation or increased dislocation density, we raise the temperature, and similar high temperature we have in case of the creep testing. So, what essentially would happen is whatever dislocations that have been introduced by the plastic deformation will be decreased. So, what would happen is there will be a decrease in the dislocation density because of the high temperature. So, how is this established? So, how is this decrease in the dislocation density happens at high temperature? So, one of the easiest way of achieving it would be annihilation of dislocation. Annihilation of the dislocations. So, what this would mean is that when you talk about dislocation, let us stick ourselves to, or let us confine ourselves to the edge dislocations. So, what we have in terms of edge dislocation is the positive and negative edge dislocations. Now, these positive and negative edge dislocations, when they travel in the same plane and under certain conditions, when they interact, they annihilate each other. So, these two positive and negative dislocations, when they interact, they annihilate each other. So, for this annihilation to occur, we need to have this positive and negative dislocation traveling in the planes that interact with each other. So, that possibility is rather very small, or it's trivial under the ambient temperature or the room temperature. However, since we are talking in the context of high temperature, what high temperature means is that we have seen in the previous lecture that high temperature activates new slip systems. So, it activates new slip systems. It also increases the mobility of dislocations. So, it activates new slip systems. It increases the mobility of the dislocation, and it also helps in overcoming any obstacle. So, the high temperature in terms of the mobility of dislocations, it helps in overcoming any obstacles that is present in its path. It also increases its mobility. It activates new slip system. So, therefore, a given edge dislocation, instead of propagating in one slip system, now has the possibility of propagating in several slip systems. So, now when there is increased mobility and the dislocation is propagating in different slip system, then proportionately the positive and negative interaction increases. So, because of the high temperature, because of the ability of the dislocation now to propagate in different slip system, because of its ability now to propagate in with increased mobility, the positive and negative interactions that ultimately leads to the annihilation of dislocation proportionately increases, and therefore with increase in temperature you are able to reduce the number of dislocation density. So, this is something that is commonly observed in annealing, and the rate at which the rate at which this decrease in energy is achieved, or this decrease which is proportional to the decrease in the dislocation density, is expressed in terms of the Arrhenius-like equation, wherein the Q is the activation energy, K is the Boltzmann constant, and T is the temperature. So the rate at which there is this decrease in the energy, so one way is through the annihilation of the dislocation. The rate at which this happens is proportional, or this can be expressed in this relation, meaning whenever this T here is the temperature, so whenever there is an increase in temperature, there is an increase in the rate of the annihilation or the decrease in the energy. So with increase in the dislocation density, this energy system's energy increases. So in general case, we do annealing to reduce its energy, but in case of creep behavior, we already have a definite temperature. We already have a temperature that is above the room temperature that will allow the whatever mechanism that happens in creep into the current system. And one mechanism is the annihilation of dislocation. And this annihilation of dislocation requires positive and negative dislocation interact with each other. The way one could achieve that is through the high temperature, because high temperature activates new systems, so that would mean the interaction will be more, and also the mobility and the ability to overcome the obstacle also increases. Again, this will enhance the interaction, thereby enhancing the annihilation of the dislocation. So by this one can reduce the number of dislocation, thereby reducing the energy. And also ultimately, for our purpose, when you reduce the number of dislocation, your new dislocations that are being formed are easy to move. That means the plastic deformation becomes more pronounced. So we saw during the transient period, the plastic deformations were restricted because the increase in the number of dislocation densities impeded each other, and therefore they impeded the overall plastic deformation. Now that by virtue of the temperature that we hold this material to, there is a decrease in the dislocation density. That means the newly forming dislocations can propagate easily, or the existing dislocation which have not been annihilated, they can propagate easily. Ultimately, that means that because of the temperature you are in, the plastic deformation is now enhanced. Now, in addition to this annihilation of the dislocation, there is also another way through which the number of dislocation density is reduced, or the energy of the system is reduced. So this involves rearrangement of the dislocation. So in addition to the annihilation, you have rearrangement of dislocations. So what this essentially is, if you talk in terms of the energy of the system, what this essentially is that you have different dislocation that have not been annihilated now, but you have provided sufficient energy to that dislocation. You have made them to move easily through the high temperature that you have held your material to. So instead of annihilating, these dislocations then rearrange themselves in order to reduce the overall energy of the system. So what you are essentially doing is you have provided energy to the dislocation to rearrange them in a convenient manner, so that the overall energy of the system is reduced. So this is something that you could relate to the general property of the material. That is, when you keep a material and you provide the sufficient mobility to it, what essentially happens is the material will rearrange itself to reduce its overall energy. That is essentially what is happening here. You have some dislocation that have not been completely annihilated. Now these dislocations are of energy, or you have provided sufficient energy for this dislocation to rearrange themselves, and they rearrange themselves in such a way that now the overall energy of the system is reduced. Now this is also one of the ways that the annealing establishes its purpose. So annealing wants to reduce the energy of the system. So this is also achieved by rearranging the dislocation. Now let us see what this rearranging means. Now when we talk about, let's stick to this simple edge dislocation. When we talk about this edge dislocation, something like this, you have an extra row of atoms in this region, and that causes a compressive strain, or let's talk about in stress. So it causes a compressive stress because you have an extra row of atoms. So that is how you define your edge dislocation, as you have an extra row of atom above a certain plane, and that extra row of atom would introduce a compressive stress. And below that definite plane, you have a tensile stress acting below that plane of atoms. So the edge dislocation as a dipole. At the one end it comprises of, or it introduces compressive stress, at the other end it introduces tensile stress. Now if you have an array of dislocation in a given plane, so an array of dislocation in a given plane, so that means in this plane you have all the compressive load, compressive stress acting in a particular region and all your tensile stress acting in a particular region. So there is an accumulation of, when you talk about when you distinguish the region with respect to this plane here, then in this region below there is an accumulation of tensile load and here there is an accumulation of the compressive load. Now given that you have provided sufficient amount of mobility to the materials, or rather the sufficient amount of mobility to the dislocation, and you have thereby allowed the dislocation to rearrange themselves to reduce the overall energy, one possible way for them to rearrange is in this manner, wherein you have your tensile load acting here, the compressive load acting here, and you have your correspondingly compressive load and the tensile load, and similarly your tensile load and the compressive load. So instead of being arranged in this manner, now they have piled up one over the other. Instead of being piled up horizontally, they have now piled up one over the other. So let me try to distinguish the dislocations from the load. So this is your dislocation. So instead of being arranged horizontally over a plane, now they have started piling up one over the other. The reason, or what are the factors that facilitate such piling up, is because you have provided sufficient energy through the high temperature, either be it in annealing or be it in creep. You have provided sufficient energy through annealing. So in order to reduce the overall energy of the system, instead of being aligned themselves in the one single plane, now they have piled up one over the other. So what essentially this does is, the amount of tensile stress that is being introduced by one edge dislocation is being compromised by the compressive stress that is introduced by the other. So these pair up and they tend to reduce the energy introduced in the system. So essentially by rearranging the way the dislocation exists in the material, we have, or it is possible to reduce the energy of the system, and this is only possible when you have sufficient mobility. So this arrangement requires sufficient mobility. This rearrangement requires sufficient mobility, and this is offered to us through the high temperature under which we are studying our material. And so in addition to the annihilation, we are now able to rearrange the dislocation, or the system itself rearranges the dislocation in order to reduce the overall energy of the system. So if you look into these two arrangements, in addition to the gliding that happens along this direction, along the horizontal direction, so this is the gliding of the dislocation that happens along this direction, you need to have something called as climb, meaning for these set of dislocations to arrange themselves in this manner, in addition to the glide that happens along the horizontal direction, you need to have climb, or the climb in the vertical direction, so as to establish an arrangement like this. In order to establish a pile up like this in the vertical direction, you need to have, or the dislocation needs to climb one over the other. So this climb in the dislocation requires sufficient amount of vacancies, and we have seen that the concentration of vacancies with respect to the overall concentration also increases with temperature. So here E is the energy required for the formation of vacancy, T is the temperature. So with increase in the temperature, the concentration of vacancy increases. With increase in the concentration of vacancy, now instead of gliding in one particular plane, the dislocation can move one over the other, they can climb. So instead of gliding, they can climb, and once the climb is possible, then instead of this regular arrangement or this confinement or this setup of dislocation in a single plane, you can end up with a piling up one over the other. So this rearrangement is possible by virtue of the mobility that is enhanced by the high temperature, and also through the increase in the vacancy concentration that is also made possible through the increase in temperature. So through the vacancies you have established the dislocation climb, and through the mobility you have established a dislocation glide. So combination of these two will establish these array in the vertical array of the dislocation. that will reduce the overall energy by compromising the tensile component and the compressive component. And this arrangement of dislocation is nothing but the subboundaries. These are nothing but low angle subboundaries. So let me make it as visible as or as legible as possible. Subboundaries. So this way of arranging the dislocation will ultimately lead to the formation of subboundaries or the low angle grain boundaries. So what we have done is, by introducing high temperature, we have increased its mobility, thereby enabling the atoms or the dislocation to glide, and we have also increased the vacancies, so the dislocation can climb. Therefore, we have provided the energy for dislocation to rearrange themselves to reduce the overall energy of the system, and they have arranged themselves in this manner, and because the stress tensile and the compressive components compromise with each other, they compromise the energies. So you ultimately end up with a low energy state, and by forming what we call as the sub boundaries. Now sub boundaries, what they essentially do is, they essentially reduce the formation of formation of sub boundaries. So let's call them as sub boundaries. So once you have sufficient amount of sub boundaries, what happens is that the number of dislocations in the actual grains decreases. So instead of the dislocation being dispersed all over the grains in the polycrystalline system, you have now compiled them, arranged them into a definite sub-boundaries. So the dislocations have now accumulated and formed the sub-boundaries. So that means the remaining areas of the grains are available for the newly formed dislocation or the existing dislocation to propagate. So that means the formation of sub-boundaries by the rearrangement facilitates or rather enhances plastic deformation. So in addition to the annihilation of the grain dislocation, we saw the rearrangement of the dislocation. So annihilation, ultimately it is quite straightforward. The annihilation decreases the dislocation density. Now in case of rearrangement, the number of dislocation within the grain is reduced because the dislocations that are existing get accumulated and form the sub-boundaries. That means once your sub-boundary is formed, it is confined to a specific region of the grain, and in the remaining region the dislocation density has sufficiently decreased, and now the existing dislocations can move freely, and new dislocations that are being formed can also move freely. So in this way, what we have done is, we have enhanced the plastic deformation of the materials just by virtue of the stress. When you just talk about the stress component, when you increase the number of dislocation densities, the plastic deformation is impeded. Now with because we have considering increased temperature, we have decreased that dislocation density by the annihilation and the rearrangement. So if you want to compile these two, so because of the stress component, the dislocation density increases. Because you keep on imposing the stress, the new dislocations begins to form and they interact and they impede each other. So this ultimately restricts the plastic deformation. However, because of the high temperature that we consider, the dislocation density decreases because we have annihilation and also the rearrangement. Now incidentally, the rearrangement is also referred to as the polygonization. I'm not going to write the whole term here, it's a bit getting tedious. So it's polygonization. So this is what the rearrangement does. So this rearrangement, or ultimately the polygonization, involves the climbing up or the rearranging the existing dislocation in order to form the sub-boundaries. So while the stress increases the dislocation densities and impedes or restricts the plastic deformation, the high temperature, what it does is, it rearranges the existing dislocation in such a way that the dislocation density within the grains is reduced. In addition to that, it also annihilates certain dislocations that are existing within the system. So that these two do the things that are contradicting to each other. Therefore, this balance between the stress and the high temperature. So when there is a balance between these two, that is when we talk about with respect to the dislocation or the plastic deformation, when there is a balance that is achieved between the effect of the stress and the effect of the high temperature, you would end up with the steady state conditions. Or rather, this is your strain, this is your time, and this is your steady state condition. So this steady state condition, or the third stage of the creep behavior, is established by the balance between the stress and the high temperature. The stress increases the dislocation density and it impedes or restricts the plastic deformation. However, the high temperature, it decreases the dislocation density by annihilation and by polygonization or rearrangement. This rearrangement essentially forms the low angle grain boundaries or the sub boundaries, thereby accumulating the existing dislocation and leaving room for new dislocations to form. Now, in addition to that, when you keep on holding the material at high temperature, even the different low angle grain boundaries or the sub boundaries, they also move and coalesce even more, sufficiently reducing the dislocation densities. So all these are possible because of the high temperature. So these two, stress and the high temperature, since they have contradicting effects on the material, the balance between the two establishes the steady state condition. Now ultimately, when the influence of the high temperature becomes more pronounced, or the plastic meaning the plastic deformation becomes more pronounced, the plastic deformation is now allowed to run wild, then this would ultimately lead to the final stage that we saw, that is the ternary state or the accelerating creep state, and that would mean that the plastic deformation would increase, and the slope of the strain would sufficiently increase, leading ultimately to the failure of the material. So this would be your accelerating creep stage, and in this stage the effect of the high temperature, that is the enhancement or the dominance of the plastic deformation, get sufficiently increased, and that means the material continues to deform plastically, ultimately leading towards failure. So we saw that in the initial stages, in the stage 1 and stage 2, the effect of the stress is more pronounced. So therefore, in the stage 1, you have your behavior that is similar, that you can relate it to your regular stress strain curve. And in the stage 1, you have that is the instantaneous creep stage. You have your behavior that is that is relatable to that of the mechanical behavior involving stress strain curve. That is the same carries over to the stage 2 or in the transient creep stage, wherein because of the stress that you impose, the mechanical or the dislocation density proportionately increases. Because of the increase in dislocation density and the complexity in their interaction, their movement gets impeded, thereby restricting the plastic deformation. So all these happen at the stage 1 and stage 2 of the creep. Now when you move on to the stage 3, it is where the influence of temperature begins to get dominant. In stage 3, the influence of the temperature and the influence of the creep are at their balance. So while the stress wants to increase the dislocation density, impede the plastic deformation, the temperature wants to reduce the overall energy of the system. It annihilates the dislocation, it rearranges the dislocation in such a way that you have formation of sub-boundaries, and you ultimately leave enough room for the maneuvering of the other dislocations. So all this happens because of the high temperature, or the facility or the energy rendered by the high temperature. So there is a decent amount of balance between the condition introduced by the stress and the condition introduced by the high temperature, the later that it favors the plastic deformation. So therefore, while the stress condition impedes plastic deformation, the high temperature condition favors it, so you have a balance in the steady state creep region. However, even more as the time increases, the effect of the temperature, that is the favoring of the plastic deformation, gets more pronounced towards the end, and ultimately because of the exceeding amount of plastic deformation, ultimately your material fails, and that is what you observed in the accelerating creep stage or the tertiary creep stage. So these are the factors that contribute to, or that are responsible for, the different creep stages that you see. So in addition to these factors, or and along with these factors, you can categorize the different creep behaviors depending on the materials that we look into. For different material, the overall creep behavior might be different, but in case of crystalline material, from the aspect or the perspective that we were talking about so far was from the perspective of plastic deformation or from the perspective of number of dislocation. So this is possible for us to do because we are talking about the crystalline material. For the non-crystalline material, the behavior correspondingly varies. So far as the crystalline material is concerned, these are the factors that govern the different stages of the creep. Now we saw that with respect to the temperature in this expression, with respect to the temperature here, and also for the overall annealing rate, we saw temperature plays a vital role. Now from this you can also conceive that, you can try to think about and conceive that how a increase in temperature, how a decrease in temperature would affect the different sections of the creep curve. We saw only when you have sufficient amount of temperature, you introduce sufficient mobility to dislocation, you introduce sufficient vacancies for the dislocation to climb. So you have a rearrangement of the dislocations, thereby allowing enough space or reducing the overall dislocation density. Supposing if your temperature is further increased or it decreased, now you can understand how it would affect the different stages of creep. So having just introduced the different factors that govern we have not looked deeper into the different material, just given you an overview, a restricted overview, just focusing on the crystalline material. So we have seen with respect to the crystalline material so far, what are the different material changes or the factors within that occur in a material, or the changes that occur in a material. What are these changes that are responsible for the different stages of creep? So which factor contributes to what stage of creep, or which factor is dominant in which stage of creep, is what we have discussed so far. In the subsequent lecture, let's talk about the overall creep mechanism and see if we can quantify the different curves or if we can quantify these different stages. So in the next lecture, we will be talking about we will not be taking just the phenomenological view of treating the different stages separately. In the next lecture, we will be talking about the overall creep mechanism and how a material would exhibit during the overall creep behavior. So let's see ourselves in the next lecture. Goodbye.